Connect this down. I think we're still maybe getting one, maybe two new students this week. Oh, next week, is it? Who told you this? Your tutor, is it? Huh? Oh, friend told you, okay. It's not going to be until next week. Okay. Right, so rocket science then. Okay, so another way to state Newton's second law, well, okay, before we do that, what is Newton's second law? What way did we state it previously? Yeah, and as a formula? Simply F equals ma. Yes. There's actually another way to state Newton's second law, which is like this. And let me explain what each part means. Newton also said that F is the change in... Does anyone actually know this letter, what it represents? Pressure. Good guess, not pressure. Momentum, yeah. It's a change in momentum over the change in time, where P is the change in momentum per unit of time. So what exactly is momentum then? Momentum P, I'm sure somebody, at least one person would know this. Does anyone know momentum? You actually were mentioning momentum last week. Do you remember the formula for it? No? Do you remember it? MV. Yeah, momentum is the product of mass and velocity. So, does that make momentum a vector or a scalar? It's a vector. Good. It's a vector. That is P equals mv, and what are the units? The units. Very good. Kilogram meters per second. With units, of course, kilogram meters per second. And in a moment, I will prove that this is actually the same as F equals ma. So, this is your first lecture. So what I usually say to students is, you don't have to write everything. We should write down the most important things. So, for example, on this slide, what is most important is saying momentum P equals mv. So you should write down this word because maybe this is a new word for you. And of course this formula you should write down then. Okay, continue? Yes? Is it okay if I can continue, if I change this? If you need a minute, just tell me. Yep, that's no problem. What class did you have this morning? Or did you not have class? Tutorial? Group tutorial?
Yeah.
With Lorraine?
Yeah.
I told Lorraine to say to the physics students we have class at 1, just to make sure. And she replied to me saying, oh, I don't have the physics students this morning. So everybody's out to get me. Said, oh, I don't teach the physics students this morning. I'm like, okay, I thought you did. Alright. Okay, ready now? Yep. So, let's prove that it's actually the same formula. So, F equals the change in P over the change in time. So, I'll draw a little picture here. We start off with M, and it has a U, and this is at the beginning. And then it increases to V, and this is, some time t has passed. So what is the change in momentum? Well, that's the momentum at the end minus the momentum at the start, and the change in the time is t2 minus t1. So what's the momentum at the end? What would that be here in this picture? What would it be? Maybe mv, yeah? Minus, and the momentum at the start? mu. Over t minus 0. So this I can write as mv minus u over t. Now, this should look familiar because on the top is the change in the v over the time. Like, what is this piece here? A, yeah. So this is equal to ma. So in fact, this formula is the same as this one. Yeah. Wei, have you studied any physics before?
No.
Like even a little bit? What? Oh, sorry. Apologies.
Wait.
Sorry. You are...
Woogie.
Huh?
Woogie.
Oh, that's a hard name. Have you studied any physics before?
No, it's first.
Not even a little bit?
I know a little.
A little bit.
Like I know this formula.
You've seen this formula before, okay.
It's just things that I know.
In middle school?
Yeah.
Or high school?
In middle school.
Middle school, yeah, okay. Alright, did you please write this proof down fully?
Yeah.
Got that? Do you, the person that's coming next week, are they your friend or you just know them or?
In business, right? And you want to switch to engineering.
Oh, I don't know about this person. This is new.
Oh.
Why do they want to switch?
He doesn't like this class.
That's a good reason. But what does he want to study? Do you know next year?
No idea.
No idea. Could still be business. Don't know. Okay. All right. Continue. Yep. So, why bother with this formula if F equals ma works? Like, why bother using this if we can already use this? Well, the reason is it's very convenient to use when the time is actually very small. This is one reason to use it. Or another reason we might want to use this new formula is if we want to calculate something called the impulse. Now, does anybody know this word impulse for physics, what it means? Impulse? Very good, yeah. The impulse is just another name for the change in momentum, which is delta P. That's all. So that delta P on the top is actually called the impulse. Now, why is the impulse important? Impulse is important because impulse is what hurts. What I mean by this is if you hit into the wall, okay, it's not the force that hurts you, it's not the acceleration that hurts you, it's the impulse that hurts you. It's how much your momentum changes. That's what hurts, okay? Because I could hit you with a big force, but if I do that for a small time, that's not so bad. You know, a big force but for a small time is okay. You know, but a small force for a long time could actually maybe even be painful. It's the impulse that hurts. You know, when a car crashes or two cars crash, the reason it's so bad is because the impulse changes so much. The car is moving very fast, and then it's not moving, and that's the problem. It's the change in the impulse. Okay, so in my head, impulse is the thing that hurts. So if you write this definition down, we'll have a look at some examples before continuing. So impulse is just the change in momentum. Continue, yeah. Right. So here's a very, very simple example I want you to do. A 1,200 kilogram car crashes into a wall at a speed of 20 meters per second and is brought to rest. What was the impulse? Okay, so calculate this for me, please. Oh, you could nearly do this in your head. What is the answer? 24,000 and the unit? Yeah. Kilogram meters per second, yeah. So the impulse is 24,000 kilogram meters per second. Yeah. Now, just before continuing, so the answer here for this one is, and I suppose we should say it's a minus, because if we think about it, oh no, sorry, that's wrong. MV minus MU, and the V is 0. Yeah, no, it is a minus. Yeah, the minus just because the impulse is backwards. Car is brought to rest. Just another point here. If I say F equals delta P over delta T, that means F delta T equals delta P. What's the unit here? We said it's kilogram meters per second. What's the units here? If you look at this, what's the units? Newton seconds, actually, yeah. They're the same units, okay? So Newton seconds is the same thing as kilogram meters per second. It's maybe worth remembering that. Yep, okay. Here's another one. A hammer hits a 100-gram nail with a force of 50 newtons, and then as a result, the nail moves with a velocity of 4 meters per second. How long was the force applied to the nail by the hammer? So the hammer hits the nail. I want to know how long was the contact between the hammer and the nail. Okay, so I'm looking for the delta T. The delta T. Okay, try it. I'll do it in one moment. This one's a little bit harder. I can draw the picture if you want. What you have is you have a nail, and the nail is 0.1 kilograms, and then a hammer applies a force, and the force is 50 newtons. And as a result, it causes the nail to start to move downwards with 4 meters per second. Okay. Do you want the picture or the words? Which is better? Picture? Okay. Give me the time here. That's what I want. You have it, yeah? Yeah. We'll give them a minute. That's 0.1 kilograms. So the formula I'm using is F equals delta P over delta T. So that means delta T equals delta P over F. Now, the F we know, that's a 50. Although, if you want, maybe I should call that minus 50. If I call down minus, and I call that minus 4. The change in momentum is mv minus mu. The m we know, so here we have the v minus u. What's the v? 4, or rather minus 4. And what's the u? 0. So all these minuses cancel. I'm left with 0.002. Correct? I forgot about the 4. 8. Yeah? That's quite small. What's that? It's 8 milliseconds. Isn't it? Yeah. 1, 2, 3. Yeah, 8 milliseconds. Small time. But of course it should be a small time, you know. And why is this? Did I get a positive here? Of course. Sorry, I forgot what it was, yeah. I was going to say, is it important that it's positive? It has to be positive because of the time, yeah. Yeah. Okay, continue? Yep. So, here is another one, but I think I'll skip this example because it's the same as the other two. You get the idea for this. It's just a football one. Okay, so really what I'm trying to get to is another reason to use this formula. The biggest advantage to me to using this formula is it allows you to calculate the force provided by rockets and other propulsion systems. If we think about the hot gas that comes out of a rocket, it has a mass and it also has a velocity. But the gas was at rest. The gas was at rest in the rocket, and then what happens? It fires out of the rocket. So its momentum has changed. Its momentum was zero and now is not zero. And remember Newton's third law. For every action there's a reaction, equal and opposite reaction. So whatever the downward momentum force is, that's actually what's equal to the upward force. In other words, if you want to know what the force upwards for the rocket is, you need to look at what the gas is doing downwards. So let us calculate what this up force is. We remember this word? Thrust, driving force. So let's calculate. Let's see what we got. Okay, so let's have a picture here. So here is our rocket, and the gas is inside of it. And in my head, I picture it like this. The gas is made of lots of pieces of gas, and each piece of gas I'll call delta M. And each delta T that passes, some of this gas comes out. Now for these questions we always look at the time over 1 second. What happens each second? So we'll say each second one of these comes out. Drops down here, okay? So what is the force here? Well, we said that's delta P over delta T, but for these problems we look at what happens every second. So it's actually just more conveniently this, which is mv minus mu. In this picture, what is the zero here? The u or the v? The u is zero because the gas starts at rest. So this is equal to mv then. Yeah? Now, if we're being technical, is the V positive or negative here in this picture?
Negative.
V is negative. So if you want, you can say this is minus some positive number here. In other words, that this is downwards. Okay? So there's some force moving the gas down. But Newton's third law says that there's a reaction upwards. I'll call this reaction force T, and that should equal this force here. In other words, the force pushing down on the gas should equal the force that the rocket feels being pushed up. You know, like when you push against the wall. So we have this very, very nice, simple formula that says the T, which is the force up, is just equal to how much gas comes out per 1 second multiplied by the speed of the gas that it comes out at. And that's it, nice and simple. If you know how much gas comes out per second and you know how fast it comes out, simply multiplying the two gives you the formula for the force up. As simple as that. So like I said, rocket science is not so hard. Okay? We just have to multiply two numbers and we know the force heading upwards. Yeah? And again, I just remind you that all these units are looked at on a per second basis. Mm-hmm. Okay. Can I continue? Yeah. Just to point out what is very interesting here is it actually, if you think about it, doesn't have to be a gas that comes out. It can be anything that comes out. There's a video which I will find for you. You might have even seen it before, but it's an engineer who made, he was in a river and he made a little pack here. You might have even seen this, and he has a hose that's connected up to this pack here, and there's a pump here. So what he did was the water comes in here, and then the water is fired out of this backpack, and of course you see him moving up. I don't know if you've seen this video. You've seen this one. Anyone else seen this? No. So my point is, this works for water, for gas, machine gun pointed at the ground, there'll be an up force. Okay. Right. Let's have a look at an example here. I have two important examples to do. So the first one, as the mass of a small rocket was 4,570 kilograms. At launch, the hot gas is propelled at a speed of 4,462 meters per second. No, I must have something wrong here because this number is too big. It's bigger than this number. Let me add in. I'll add in another 2 zeros. Add in 2 more zeros here. 457,000. What is the up force? Actually, you know what? You don't even need to know the mass of the... Forget about that. Pretend you can't see that number. Okay, so what's the up force here? Well, it's just 4462 multiplied by 7485. So what's that? Let's see.
83,300,000.
Pretty big, huh? Yeah, that's the force up for the rocket. Okay? Oh, that was an easy one. Now the next example is harder. Okay. It's a windy day and a physics student was walking home. The student stops for a moment to calculate the force he is feeling from the wind. The wind was blowing at a speed of 12 meters per second into the stationary student, the student standing at rest. The student is 1.6 meters tall and 40 centimeters wide. The density of air is about 1 kilogram per meter cubed. What is the force felt by the physics student due to the wind? Okay, so student walks home, student stops, they feel the wind pushing against them, and they want to know what is this force. So let's calculate this. I'll draw it first for you. Here is our student. Our student is a rectangle, roughly speaking, which the student is 40 centimeters wide and 1.6 meters tall. Okay? Now, the wind is blowing at 12 meters per second, and remember we should always look at these gas problems on a per second basis. So if I just look at the picture over 1 second. Okay, that's important. Important. Oh, forget it. Important. Okay. We don't need to look at all the wind. He only really cares about the wind which is 12 meters in front of him. Why am I saying this? Why am I saying I don't need to... His whole world is just this 12-meter box. He doesn't care about anything outside the box. Why am I saying that, though? What's my reason for this?
Because there's 1 second.
Yes, 1 second, and it's 12 meters per second. So it means only the air which is in this box in 1 second can hit him. Because the air here will not make it to him in 1 second, because it's going at 12 meters per second. So we only look at 12 meters here. Okay? So can you see that this is kind of the same as the rocket? Instead of the gas being fired out of the rocket, here the gas is being fired at the person. But that's no different, because, you know, if I have a rocket and the gas is being fired out, it'll cause the rocket to move to the left. But, you know, it's the same idea if I fire the gas, you know, at the rocket. For the rocket not to move, it must apply a force equal and opposite to cancel this. That's what's happening here in the picture. The reason the student doesn't fall back because of the wind is because they lean forward, or they push into the wind. So whatever force this student is pushing at, that must equal the force that the wind is pushing against him. Otherwise the student will fall backwards. Anyways, my point is, it's the same as the rocket example. The only difference is the gas is being fired at the student instead of the student firing gas out and moving forward. That's the only difference. Okay, so what is the formula here for the force? Well, if we use the rocket example, what would it be? It would be M for the gas, V for the gas. Now the V we know. What's the V? It's 12. But we don't know the mass of the gas. But we have this formula, density equals mass over volume. And so what does volume equal? What does mass equal? Density multiply volume. Yeah? So then this will equal 12 density volume. Now, what did I say the density was? What's the density of air? 1. So nicely, this is just 12V. Now what's the volume here? It's 12 multiply
40.
Yeah, 0.4 multiply 1.6. So that would be whatever, 144 multiply 0.4 multiply 1.6. Now I'm too tired. 0.4 multiply 1.6 multiply 144. 92.16 newtons. So there's a force here of 92.16 newtons, which means the student, so that they don't fall down, they must also be applying a force here of 92.16 newtons. And if they want to start moving, like start running, then the force must be greater than 92.16. Now 92.16, that's pretty heavy. That would be like if you lie on the ground and then have 9 kilograms resting on you. It'd be the same force as this about. How heavy is 9 kilograms? How heavy is 9 kilograms? What's 9 kilograms? Big bag of potatoes, maybe?
Rice.
Big bag of rice, maybe?
Yeah.
Can you get 10 kilogram bags of rice? Yeah, okay. Be like lying on the ground with a bag of rice on you. The same force as that. Yes?
Where's the density again?
Oh, it's in the question. Density of air is about 1 kilogram per meter cubed. So it means that if you knew how fast the wind is blowing, then you can know what force you'll feel that morning as you're walking to school. 12 meters per second. What's that in kilometers per hour? Let's see. 12 meters per second would be this many meters per hour. 43 kilometers per hour. That's a 92 newtons of force. So we'll say roughly every 50 kilometers per hour of wind is about 100 newtons of force. Yeah. What could the student do to reduce the force from the wind?
Walk
Not walk into the wind, perhaps. Yeah. If they have to walk into the wind, what would they do? Well, yes, correct. Yes. If the student leans down a bit, it reduces the force from the wind.
Walk sideways like this. Like this. They could reduce the area, not walk like this.
Oh, I understand. Oh, yeah, okay. Walk sideways, as in have this side of you. Yes, the same result, because you're reducing the area. Yes. Bit hard to see where you're going, but it does the same thing. Yeah. Okay, good. Can I continue? Yes, I think that was the last example. Yeah, it was. So, what I want you to do, just for 5 minutes or so, and then we'll continue with the next lesson. Can you begin those questions on the worksheet for a few minutes, and then we'll start the next lesson in a moment, which will be an easy lesson.